Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on average rates of change of a function. Now, this idea is not new to you. The rate of change of a function is just its gradient, and you've been calculating that for years. So you're used to seeing the gradient as the rise over the run, but we're going to look at it slightly differently here. So both of these things say exactly the same thing. So here we're using Greek letter delta. This is the capital letter delta, the lowercase letter delta. We're using this to mean change in. The gradient of a function is the change in y values, the rise, over the change in x values. So you've been calculating the gradient of a line for a long time, but it turns out calculating the gradient of a line is easy. The reason is that all lines have a constant gradient. So what I mean by constant gradient is if you were to calculate the gradient of a line between these 2 points, you'd get the same answer as if you, say, calculated it between these 2 points. The gradient's constant. Each time I go across by 1, I go up or down by the same amount each time. So that's why lines are easy to work with. But this ceases to be true for nonlinear functions. So the graph here is y equals x squared. If I want to take a look at its gradient, it's actually complicated. See, in this region of the graph over here, the gradient is actually negative. The reason for this, as x is increasing, y is decreasing, y is coming down. The change in y is negative because y is coming down. The change in x is positive because x is increasing. So negative over positive equals negative. So the gradient in this region is negative. So the gradient around the origin here is about 0 because this graph is almost horizontal at the origin. Horizontal means there's no rise, there's no change in y, so the gradient 0. Now over this region of the graph, it turns out that the gradient is positive. X values are increasing, y values are going up. As we go across, we go up. So both change in y and change in x are positive. So I'm just saying this to help you understand that in different regions of this graph, the gradient takes different values. In fact, it turns out the gradient of this function is different at every single point along the curve. So how do we calculate the rate of change? Well, what we can do is calculate the average rate of change between 2 points. So let's say, for example, I wanted to calculate the average rate of change between these 2 points. So minus 1, 1 is this point here, and 2, 4 is here. So to calculate the average rate of change, I'm going to use this fact over here. Lines are very easy to work with. They have a constant gradient. So what I'm going to do is draw a line between these 2 points. So this line here is called a secant. It hits the graph twice, unlike a tangent that hits it only once. Calculating the gradient of this line is very simple. Remember, I just used the 2-point formula, y2 minus y1 over x2 minus x1. So it's the change in y values over the change in x values. So the gradient here is y2 minus y1 over x2 minus x1. Putting that on your calculator, you get 1. So that makes sense. From this point, we've gone across 3 and up 3. X values have increased by 3, y values by 3. So on average, each time we increase x by 1, we go up 1. Cross 1, up 1. Cross 1, up 1. So that's what it's saying here. But hopefully, you're looking at this and you're thinking, okay, but this secant looks nothing like our curve. It doesn't represent it at all. What if I wanted to know the gradient in this little region here? Well, knowing the gradient of the secant doesn't help because the secant is sort of pointing in a different direction than the curve is. So why don't we calculate the average rate of change between 2 points in this region? So let's start with the point x is 1.5, so y would be 1.5 squared, and the point 2, 4. So the 0.24 is here. 1.5, 2.25 is about here. So what we're doing is we're calculating the gradient between this point and this point. So if I draw the secant that goes through these 2 points, you can see that it much more closely resembles the red curve in this region than does the yellow line. So the gradient of this secant here, same formula as before. It's y2 minus y1 over x2 minus x1. And putting that on your calculator, you get 3.5. So you can see the gradients were totally different. But this one here, this black secant here, is a better representation of the rate at which the red graph is changing in this region. What we're going to work towards with calculus is being able to calculate the gradient at every point along the curve. And to do that, what we're going to end up doing is moving these points closer and closer together. They're so close together that they're indistinguishable. That's how we'll calculate what is called the instantaneous rate of change. The instantaneous rate of change is the gradient at a single point. The average rate of change is the gradient between 2 points, which we can view as the gradient of a secant of the line that hits those 2 points. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.